So hopefully you guys all got a chance to get started with the energy transfer puzzle, but I have filled out the first table for you here in order to check whether you were thinking about the puzzle correctly. So to recap, you needed to figure out which of the species listed above in this table were producers, primary consumers, and secondary consumers. And so I listed those species here for you. For producers, I looked for all the plants. For primary consumers, I looked for all the herbivores. And then for secondary consumers, I looked for all the carnivores. Now, we didn't get to tertiary consumers in this table, but you do have a question that involves one in the analysis. So then I added up the energy that each of these species required. If you notice that it's always 500, you are correct. It is always 500 energy units. And that's not some kind of rule. I don't want you to get confused. It's not a rule. It's just that I wanted to make the math like so easy that you can do it in your head or quite simply so that the math isn't what trips anybody up. Now for available energy, I got some questions on this. Available energy information was up above in the background story. So in the background story, it said that there was this number of energy units that radiates down from the sun, but only 1% of that was actually absorbed by the plants. And so this 1 million units absorbed by the plants is your available energy for the producers. After that, what do you do to find the available energy for everybody else? Anybody?
It's 10%, right?
10%, yeah. So divide by 10. Also, fun fact, if you didn't know, drop a zero. 10%, if you're taking 10% from something, you just drop a zero. So I went from 1 million to 100,000 to 10,000. And then the last little piece I needed to do was figure out how many of each species of the producers, primary consumers, secondary consumers, there could be, given the amount of energy available and the amount of energy that those things need. So I just divided. I've got 1 million units available to my producers. To have one of each, I need 500 units. So really, if you're wondering why this works, I'm canceling units. So I'm dividing energy units by energy units per species. So I end up with the number of each species. So really quick, what do you notice about the number of each species on the trophic levels? How do those numbers compare? I'm looking at this number. Type it in the chat. How do these numbers compare? And what shape does it reflect? How is this tying back to what we talked about before? I'm looking at the chat and I see, yeah. So each number of organisms goes down. It's 10% of the last. And that reflects our energy pyramid, which is a triangle, right? So we expect to have way more producers than primary consumers, more primary consumers than secondary consumers, and so on. So it reflects that triangle. Now, I have a question. Which of my questions was a trick question? Whoa, just said question like 8 times. Can you guys guess, those of you who've gotten a chance to look at these questions, which analysis question did I kind of consider to be a little bit of a trick question? So in the first one, you were being asked to tell me, whoops. In the first one, you were being asked to tell me where does the 90% of energy that doesn't move on to the next trophic level go? That's not a trick question. What's the answer to that? I'm hoping somebody knows. Where does the rest of the energy go if it's not passing to the next trophic level? You can use this. Okay, yeah, so I've got heat and waste. Perfect. So this is either going to be lost as heat. Whoops. It's either going to be lost as heat radiating off here when like my rabbit's running around, it's trying to escape the fox, it's trying to get its own food, it's reproducing, it's growing, it's doing all these things that make it use energy and release it as heat. But also, my rabbit might just die of old age if he's lucky. And so that energy is never going to go to the next trophic level. So you are absolutely right that this energy goes to decomposers if the organism dies of old age or is lost as heat as a result of doing daily stuff like moving, reproducing, ... If you're wondering like, hey, I haven't done this puzzle yet, should I write this down? Yeah. All right, so which, actually, let's just look at the second question. So this is the one that I was saying is a trick question. Does anybody know why I think it's kind of a trick question? It's asking you, is there enough energy to support tertiary consumers like a bear or a coyote? Assuming that a coyote could feed on a fox, which makes it what? Tertiary consumer. And we're saying a coyote requires 600 units of energy per day. Why is this a trick question? How do I think about this? How do I figure out the energy available to tertiary consumers, like a coyote? Let's start there.
Is it a trick question because there's like no available energy and it's just there's absolutely no way they can support the tertiary consumers off of only 1,000 energy units?
Okay, so there's a little bit of available energy. There's 1,000. Now, is 1,000 enough for a coyote?
Only one.
One. So 1,000 is greater than 600. I'm just like doing a total math review here, in case you were wondering. 1,000 is greater than 600. Am I right? Okay. So based on what Marcus is saying, we can support exactly one coyote. Now, somebody else, somebody I've not heard from, please tell me, can I support tertiary consumers in my ecosystem? I have enough energy for one coyote.
There's enough energy for one tertiary consumer. That's it. Only one of them.
So how long, here's another way to put it, how long would a coyote population exist in my ecosystem? Is it going to be able to go on generations?
Nope, they can't reproduce if there's only one of them.
So we need 2 to reproduce. So 1 does not make a population. And even if we had 2, that would be very optimistic to hope that my coyote population is going to last very long. So in this ecosystem, I've had a lot of people telling me that, yep, there's enough. 1,000's more than 600. And you're right that 1,000's more than 600. But we need to think back to like the limiting factors conversation, to the biotic interactions. We need to be on this ecosystem level and go like, okay, is one coyote a population? Is that going to actually be supported in our ecosystem? And the answer is no. And going back to what Marcus says, in that sense, 1,000 is basically zero. 1,000 energy units is not enough for a tertiary level. So I hope that that's like helpful to you to consider some of that. The last question I want you to think about, I want you to consider these last few questions in your analysis, but I want you to think about and just recap for me right here on this slide. Number 2, why are there only like 4 to 6 in this particular food pyramid? There's 5, but why are there only 4 to 6 trophic levels on most food pyramids? Why do we stop there? If you can answer this question, I think you pretty much get this. So even if you don't want to say it to the group, self-check. Self-check. Do you understand why we cap off our food pyramids at 5, 4, 6 levels? If you've got a good way of explaining this, type it in the chat for everybody. We'll all benefit. I am very serious about that. We will all benefit from hearing this in as many ways as possible. Because I might just not know the words to teach somebody in the class well, but maybe you do. Okay, so in my chat, I see that there wouldn't be enough energy for a 5th or 6th level. Yes, not enough energy, not enough energy, particularly because, yes, Jack, because of the 10% rule, eventually I'm dividing by 10, and eventually the level at the top is gonna be like, I can't do it on like 0.125 calories, right? So when you divide by 10, you reduce that energy available really fast.